There is a device that was once a standard fixture on industrial buildings, warehouses, farm structures, and residential rooftops across the United States and Australia. It had no electronics, no motor, and consumed 0 watts of electricity. Independent testing proved it could reduce peak attic temperatures by as much as 37 degrees Fahrenheit and cut household cooling costs by nearly 15%. It was cheap, it was simple, and the physics behind it was bulletproof. They are called turbine ventilators, and if you walk through any new housing development being built today, you will struggle to find a single one. So the question this video is going to answer is not just how they worked, it is why a proven, zero-energy cooling technology disappeared almost completely from the American roofline, and whether the data says we made the right call by walking away from it. The idea of moving air through a building without burning fuel or consuming power is one of the oldest engineering problems in human history. The solutions people developed to solve it were not primitive guesses. They were the product of generations of precise, empirical observation about the way heat and pressure behave inside a structure. Persian architects working in cities like Yazd developed tall masonry wind catchers called badgers, vertical shafts designed to funnel desert breezes down into the lower levels of a building while simultaneously pulling hot, stale air out through the top. In the Tang Dynasty, Buddhist monks integrated natural ventilation ducts throughout underground cave complexes to control both temperature and air quality without a single mechanical component. And by the Middle Ages in Europe, the way a building breathed was treated as seriously as the breathing of the people inside it. Air was not an afterthought. It was a structural priority. The push towards something more active began during the Industrial Revolution. Deep mines needed a way to keep workers alive underground, and engineers responded with fire-driven ventilation systems and manually powered wooden fans. By the 18th century, the Houses of Parliament in London had installed a primitive mechanical system called a blowing wheel to replace foul air with fresh air. By the 19th century, figures like David Boswell Reed were building steam-driven ventilation systems for hospitals and barracks, where airborne disease made the movement of air a matter of survival. But all of these systems required fuel, infrastructure, and continuous maintenance. The stage was set for something fundamentally different. That something different arrived in 1910, when an engineer named Samuel Ewart patented a design for a spinning cowl that sat on top of a roof and actively pulled air out of the space below it. Ewart's original patent describes the device as a solution for both ventilation and the prevention of downdrafts in chimneys. The gusts of wind that force smoke back into a living space, unlike everything that came before it. His device had no fuel source, no electrical connection, and required no human input of any kind. It simply sat on the roof and worked. To understand why Ewart's invention mattered, you have to understand the specific problem it was designed to solve. During a typical American summer, solar radiation hits the roof surface and converts the attic into a thermal reservoir. Temperatures inside that space regularly climb past 150 degrees Fahrenheit. And that heat does not stay contained. It radiates downward through the ceiling and into the living space below, forcing the air conditioning system to run longer, work harder, and consume significantly more electricity just to maintain a stable indoor temperature. According to the United States Department of Energy, every single degree of attic temperature increase can boost the cooling load of a home by up to 4%. In many homes, the ductwork carrying cooled air runs directly through that superheated attic space, meaning the air is already warming back up before it reaches the rooms it was sent to cool. The entire logic of attic ventilation is to break this cycle before it starts. Move the hot air out before it has the opportunity to radiate downward. That was the precise engineering objective Ewart built his turbine to accomplish, and he achieved it without consuming a single watt of power. Ewart's turbine accomplished this through three separate physical principles that compound one another into a single continuous system. The first is Bernoulli's principle. As wind passes across the curved vanes of the turbine head, the air is forced to accelerate, and when air accelerates, its pressure drops. This creates a zone of low pressure inside the turbine housing that generates a suction effect, actively pulling warm air upward from the attic and exhausting it to the outside. The critical distinction here is that unlike a static vent, which simply sits open and waits for air to drift out on its own, the turbine ventilator uses the kinetic energy of the wind to drag air out of the building. The faster the wind blows, the harder the turbine works. But here is what most people do not realize. The turbine does not stop working when the wind dies down. It also leverages the stack effect, which is the natural tendency of warm air to rise. Warm air is less dense than cool air, and in a building with soffit vents at the eaves and a turbine positioned at the ridge, that rising warm air creates a gentle but continuous pressure gradient that pushes air upward and out through the turbine even when the vanes are completely still. The third principle is the Venturi effect. As air is squeezed through the narrow gaps between the spinning vanes, its velocity increases further, which reduces pressure inside the turbine housing even more and accelerates the entire exhaust cycle. All three effects compound one another simultaneously. The result is a device that generates continuous negative pressure at the highest point of the building, pulling hot, humid, stale air out and replacing it with cooler air drawn in through the soffits below. And the performance data reflects this. Independent testing found that a properly installed turbine system reduced peak attic temperatures by as much as 37 degrees Fahrenheit, producing an average energy bill reduction of 14.6%. A standard 12-inch unit moves between 250 and 350 cubic feet of air per minute at just 5 miles per hour of wind, consuming zero electricity in the process. So if the performance data was that compelling, why did the turbine ventilator almost completely disappear from the American roofline? The answer is not a single decision made by a single industry. It is four separate forces that converged over several decades and collectively pushed a proven technology into obsolescence. The first was mechanical failure. The defining feature of the turbine, its spinning head, is also its primary point of vulnerability. Over time, the ball bearings inside the unit degrade due to moisture, dust, and insufficient lubrication. When they do, the turbine produces a squeaking or grinding noise that transmits directly through the roof structure and into the living space below. Cheaply manufactured units were especially prone to this, and over the years, that pattern of failure gave the turbine ventilator a lasting reputation as noisy, unreliable hardware. The physics was sound, the manufacturing quality frequently was not. The second force was a subtle but serious engineering problem called short-circuiting. This occurs when a turbine ventilator and a ridge vent are installed on the same roof above a common attic space. Because the turbine pulls air more aggressively than a passive vent, the ridge vent can actually reverse its function and begin drawing outside air inward, bringing rain, snow, and humidity into the attic, instead of exhausting warm air out of it. The industry response was straightforward. Choose one exhaust system and commit to it. And because ridge vents are simpler to install and require no moving parts, the turbine was consistently the one that got dropped. The third force was aesthetics. Turbine ventilators are highly visible from the street. Ridge vents are shingle-over designs that sit flush with the roofline and are nearly invisible from ground level. Homeowners associations across the country restricted or outright banned turbine ventilators on the basis of curb appeal. Even in Florida, where state law protects the installation of energy-saving devices, Many associations worked around the legislation by requiring turbines to be placed exclusively on the rear slope of the roof, which frequently does not align with the prevailing wind direction and significantly reduces the unit's effectiveness. The fourth force was regulation. As American homes became tighter and more energy efficient, building codes, including the International Energy Conservation Code and California's Title 24, began mandating mechanical ventilation systems capable of guaranteeing precise, measurable air exchange rates. Because a turbine ventilator's performance depends entirely on wind speed and ambient temperature, variables that no engineer can control or certify, it fell into a regulatory gray area. It carries no UL listing and no Energy Star rating. Most building inspectors began requiring a mechanical backup system regardless, effectively doubling the cost of installation and eliminating the core economic argument for using one in the first place. So should you actually install one today? The honest answer depends entirely on where you live and what problem you are trying to solve. If you are in a hot, windy climate, the Gulf Coast, the American Southwest, or anywhere across the Sun Belt, a turbine ventilator remains one of the most cost-effective tools available for reducing your cooling load. A single 12-inch unit costs between $20 and $100 in materials. Professional installation adds between $100 and $300 per unit, depending on roof pitch and complexity. For a standard 1,500 square foot attic, 2 units is generally sufficient, and in a southern climate, the energy savings can pay back the full installation cost within 3 to 5 years. There is an additional benefit that rarely gets mentioned. Proper attic ventilation prevents shingles from overheating and stops the roof deck from trapping moisture, which can extend the functional lifespan of your roof by several years. In a hot climate, a turbine ventilator is not just a cooling device, it is a roof preservation investment. But in cold climates, or in homes built to modern high-performance envelope standards, a turbine ventilator is probably not the right tool. In winter, internal moisture can freeze the vanes completely solid, shutting the system down at precisely the moment ventilation matters most. And in an airtight home where a mechanical ventilation system is already managing air exchange with precision, adding a passive exhaust point can disrupt the pressure balance the system was engineered to maintain. For most homeowners who are building new or re-roofing, a full-length ridge vent is likely the more practical solution. It delivers roughly double the net free ventilation area of 3 14-inch turbines, with no moving parts, no bearings to fail, no noise, and no homeowners association objections. It simply works, year after year, without asking anything in return. The turbine ventilator did not disappear because it stopped working. It disappeared because aesthetics, liability, and standardization made it inconvenient for an industry that had already moved on. The physics that powered Ewart's original design in 1910 has not changed. The thermal problem it was built to solve has not changed either. Whether you install one or not, understanding how your home moves air is the first step toward controlling what that air costs you. If you want to take that logic further and see how the same principles of thermal buoyancy can cool an entire home without any electricity at all, watch our video on the solar chimney next.